Okay, we are very happy to welcome Stefano Galatolo from the University of Pisa. The title of the talk is Linear Response Theory, what it is, why it matters, and how it extends to non-autonomous systems. Please.
Thank you. I'm very happy to be here and having the occasion to tell you these things. And so let me start. Uh, uh, okay, now it works. So what I would like to do in the seminar is to let me move. Oh, I have the Zoom window which is covering okay, the interface of the okay, now it works. So what I would like to do is first to introduce what is linear response, kind of quite elementary introduction to say what is the problem we are considering. And so in the first part of the seminar, I will just speak about autonomous system, what is linear response, and why it matters. Also because there are many inverse problems related to linear response, which are very important for in the applications. And then we will go to the non-autonomous case, and we will say why the non-autonomous case is also important. And we will see from this recent paper uh, an extension, like a general theory that will allow us to write and prove some linear response formula for truly non-autonomous systems. Non-autonomous system in the sense that the dynamics change in the time and it may change in any way. And this is based on a recent preprint we put online with Valerio Lucarini in the beginning of this spring. So let us go to classical case of linear response in for autonomous dynamical systems. Now, to keep things simple, I will give the definitions for deterministic dynamical systems. But everything I will say has can also be said for many classes of random dynamical systems. Now we will see the invariant measure are important, blah, 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 and the linear response will be how the invariant measure that we are interested to study will change if we change the dynamical system. The same thing can be said for random dynamical system. In this case, you have the stationary measure, and so on and so on. But I will not make the whole theory for the both cases because I want to communicate the ideas. So I think the simplest framework is to consider deterministic dynamical systems. And so let us consider a deterministic dynamical system on a certain phase space X, which can be a metric space, a manifold with boundary, and so on and so on. I start from the very beginning from the ergodic theorem, but probably it's not necessary to really talk about the ergodic theorem to this audience. What I mean is that I'm mentioning now, I'm recalling now that invariant measures, which are fixed points for the push forward associated to the map defining the dynamics, these invariant measures are very important because they govern the behavior, the statistical behavior of observables, and the long time average of observable will converge to the space average with respect to the invariant measure for typical realizations of the evolution of our system. And so since in real life one usually can observe the behavior of the system by observing some observable and the behavior and the evolution of this of one observable, of a collection of observables, and so on and so on. and one is interested in the behavior of this, then the behavior of invariant measures is important. But as you know very well, given a map, typically there can be many invariant measures for the map, and it's a problem. However, in this big set of possible invariant measures, also typically for important classes of dynamical system, there is a few of them, only a few of them are physically interesting. And these are the physical invariant measure. There is a big theory about physical invariant measure. I will not enter in, but typically, again, the physically interesting invariant measure are among the most regular ones in the set of invariant measures. So the interesting invariant measure will be the most regular invariant measure for the map. And in many important cases, given one dynamical system, there is only one invariant measure which is physically interesting, and this is quite regular. And so we can find the interesting invariant measure as a fixed point of the push forward if we restrict the push forward only to regular enough measures. This is a first observation, so we can set up think about a situation in which, given a dynamical system, there is only one invariant measure that we are interested in, and this is regular in some sense. So to set up a theory that will formalize this general idea, typically what people do is to consider this transfer operator approach and start from the beginning to restrict the study to a class of regular measures. So what is this idea of the transfer operator approach? Essentially is, instead of we look to the behavior and evolution of a dynamical system, instead of looking how the dynamical system move points, we look at how the system move measures. So essentially we are considering the dynamics of this push forward map, but there is an important observation, which is the following. If we consider our push forward on a Banach space of regular measures, this will be a Banach space, and this will be something that move the measure. The classical push forward, which at the beginning is defined for probability measure, can be extended with the same formula to a function taking a measure. Of course, when I say Banach space of regular measure, I mean a normed vector space, which is a Banach space. So it must be measured with sign or complex valued measures, something like this. Okay, so this is a vector space. So inside the space, there will be positive, negative measures, and so on and so on. With the same formula that define the push forward, we can define another function that we will call transfer operator. Why we change the name and we say operator? Because once you consider this function, not only this function take a measure with sign and give you as an output a new measure with sign, but on this vector space, the function will be linear. Okay? That is why we call it operator. And the invariant measures will be the fixed point of this operator, which are probability measures. Now, if you choose, in many situations, in many cases, if you have a certain system and you choose carefully your space, we will often have a unique fixed point, which is a probability measure. This will be like the physical measure of the system. For example, classical example is probably this is the example where the whole theory starts from. If you have a dynamics on the unit interval and you have a map which is piecewise, no, I draw it wrong, which is piecewise expanding, for example, something like this. And this is the interval, and this is a certain map which is piecewise expanding, and the system is topologically indecomposable. Know that if you let the dynamics and the transfer operator to act on the set of measures having a density which has bounded variation, then there is only one invariant measure in this set. This is the most regular one along the possible invariant measure for this system. So the idea is consider the transfer operator on a certain Banach space of measures and find invariant measure there. And probably many cases, in many interesting cases, there is only one. To make the theory work, people usually consider the action of the transfer operator not only on one space, but they, for many reasons that probably will appear already in this seminar, usually we consider two spaces. One which will be called the strong space. In the case of piecewise expanding map, this is the strong space. Densities having bounded variation, and we also consider the action of the transfer operator on a weaker space, another Banach space with a weaker topology, which in the case of piecewise expanding maps is the space of measure having a density in L1. So usually the theory of the transfer operator approach, then what is doing? You consider only measure having a certain regularity, you consider two Banach spaces, and you let the dynamics move measure in these two classes, and then you start playing with this operator, and you start trying to understand the functional analytic properties of the operator. You find that that these operators are good. For example, many times you are led to prove that the transfer operator acting on the strong space has some compactness property, like so-called quasi-compactness, which is a kind of small perturbation of a compact operator, and so is a good operator. It will have a spectrum which is stable under perturbation, and so you can find a lot of good. You can prove a lot of good things about the dynamics of the system. Let me also say that okay, now again, to make things simple, in this seminar I will only speak about spaces of measures which are absolutely continuous with the Lebesgue measure. But everything I said can be generalized to more complicated spaces, including also singular measures and fractal attractors and so on and so on. And this is what is called the theory of transfer operator on anisotropic spaces, which are spaces of Banach space of distribution, which includes singular measures. But this is a kind of a technical complication that will not introduce different ideas. So I will skip this. I will keep the framework in the most simple situation. So I will only speak about regular invariant measure, regular measure, even from like the Lebesgue point of view. They will be always absolute continuous measure that I will consider. But again, the theory can be extended to a more general framework. Okay, so what we are going to talk about, what is linear response? Linear response is an answer to the following natural question. Okay, we know that if we start with a certain system, we will have a certain invariant measure, which is the good invariant measure for the system. What if we change the system? We apply a perturbation on the system. You will have a new system, and probably if the perturbation is good, the new system will be in the same regularity class of the old system, and probably you will have another invariant measure in the same regularity class. But it will be a little bit different from the initial invariant measure. And what we want to understand is the dependence of the invariant measure on the perturbation. In many cases, you can prove, for example, if you make a small perturbation to the map, then the invariant measure in the regular invariant measure will change continuously. There are also cases in which this doesn't happen already in the piecewise expanding case, but people try to look for example, to statement like if I perturb the system a little bit, then the measure will be perturbed just a little bit. This is called statistical stability of the system. If you prove this, you prove that the system is statistically stable because the invariant measure will change by a small amount, and then the average of the observable will change accordingly by just a small amount. Linear response is one step beyond this. Linear response is when you try to study this change and you try to prove that the change is not only continuous, but is also smooth. And you change the system a little bit, and the invariant measure will follow the change smoothly. And not only you want to prove that this change is, for example, differentiable or C1 or something like this, but you also want a formula for the derivative. And the formula for the derivative is what is really important in the application, because once you have the formula, you can try to solve it and find the things that you may be interested. And this will be important also for the inverse problem, but we will see this later. So suppose we are in this situation, we change the map, then we will change the associated transfer operator, then we will have a family of invariant measure. Is this family changing differentiably in some sense? We are thinking about a differentiable change inside a Banach space. And can we have a formula for the direction of change of the measure? Maybe from the direction of change for the map, a formula for the direction of change of the measure. This will be the linear response formula. And how to set up the problem? Of course, you look for incremental ratios and whether these incremental ratios, they have a limit. So in general, if we are in the framework that we described, there will be a family of systems, so a family of transfer operator that they are changing under the perturbation. Then we look for the fixed point, which are probability measures, so normalizing. And we hope that there is only one, but in many cases there will be only one. And we try to see if they change differentiably. We can see it by taking this limit. This is the limit of the incremental ratio of the change of the measure when you apply the perturbation. Of course, this is a limit that you are taking on a Banach space, so you have to decide which topology you are interested in, and we will see that in the framework that we have given there is a strong space and a weak space, typically people can prove this convergence in the weak topology. So, for example, it will be, let's say, the easiest thing is to prove this convergence in L1 for uh, in a situation that we said before. What this has to do with observables? This is very simple. Suppose now we are particularly interested in some observable and we want to have an idea of the first order change of the average of the observable. So we want the derivative with respect to epsilon of this integral. We have the convergence that we defined before, the convergence of the linear response. You can have the convergence also for this. Why? Because, of course, you start writing the incremental ratio for the average, but everything here is linear. If the observable is smooth enough with respect to the convergence, to the topology in which this guy is converging, then this limit will be equal to this limit. Again, if phi is smooth enough, you need you need something here, okay? But if you have if you prove the convergence of this in the right topology, you can go from this to this, and then you discover that the derivative of the average of the observable is nothing but the integral of the observable with respect to the linear response. Again, notice that maybe these will converge in some measure space, like in L1. So you only need the observable to be bounded, but maybe you can prove this convergence in a distribution space, and then you can deal with the smooth observable and everything will work. Okay? So here there is a relation between observable and topology of the convergence, but the formula is very simple. The linear response will give you the derivative expressing the first order of change of observables. Now, how to prove this linear response formula? How the linear response formula look? So now we are saying what you need to prove something like this. So in order to show you what are the main ingredients, I will do a kind of heuristic argument in which the ingredients will be the important ingredients, even for the rigorous for a rigorous approach. So, so let us see how this linear response formula look like and how can be proved. Now, suppose you have a family of transfer operators, and suppose this will be important that the family itself changes smoothly. You need, of course, if you change the transfer operator discontinuously, you cannot expect that also the invariant measure will change continuously. If you want smooth things, you have to start with smooth things. So we consider a smooth family of operators. Smooth at the first order, so we will suppose that our family is a kind of starting operator plus a first order term. This will be the derivative, telling you the direction in which the operator are changing, plus something which is of the order of epsilon. Of course, what this means in a mathematical situation, and this will be a family in an operator space, you have to define the topology for which the difference between this and this is of the order of epsilon in a suitable way. I will not enter in this topic here, but suppose you can do it in some sense. And for every one of these operator, you have a fixed probability measure. And suppose that this is also changing smoothly, so there will be the initial invariant measure, the direction of change, which is the linear response, plus something that is not so relevant.
Are you assuming uniqueness? How do you choose this f epsilon?
Sorry, uniqueness. Yes, let's suppose uniqueness for the moment. You can prove it in many families of cases. For example, for expanding maps, the easiest case is that you have expanding maps on the circle. The strong space will be the Sobolev space W11. And for every expanding map, which is, let's say, C2, you have only one invariant measure with density in the Sobolev space. Then you change the expanding map. If the change is good enough, the new map will be still expanding, and there will be, again, only one invariant measure with density in W11, in the Sobolev space. So this is, you can suppose this is unique. Many cases you can prove it. Also, for random dynamical systems, if the system is indecomposable, there is always only one stationary measure. These happen, for example, where the noise is unbounded and you can be sent in one step everywhere in the space and so on and so on. So this assumption is quite natural. Okay? So let us suppose that there is only one fixed point. Of course, this will be a fixed point in some space that I like. When I was talking about expanding maps, of course, there are many more invariant measures, like based on periodic points, but they are not regular enough to be considered in my framework. In the expanding case, for me, the good space will be a Sobolev space, W11. Okay? And here you have only one, because the system is mixing and so on and so on. Okay? So let's derive the linear response formula. Let's start from the basic identity. This is the identity expressing that f epsilon is an invariant measure for the transfer operator. Let's start and take the derivative with respect to epsilon on both sides of the equation. When you take the derivative of this with respect to epsilon, you expect a term like this. This will be treated as a product of an operator and a vector, and this will split into the initial operator times the derivative of the vector plus the derivative of the operator. This L dot is this one. Time plus the derivative of the operator times the vector. And on the right hand, we will have the incremental ratio, the derivative of this with respect to epsilon, which is f hat, the linear response. Now, from this, it's very easy to put this here and this here and transform this equation into this. Now, if you suppose that this 1 minus L naught is invertible, you can also put this operator on the right side, and you get this formula, saying that the least response is what? Is something like this. You take the initial invariant measure, you put it in the derivative operator. This will tell you how the initial measure will change when you apply the change. Then you put this in this operator, which will be is called the resolvent of L naught in 1. And the result will be the first order change for the invariant measure. Let's stop a moment to look at this formula, which is so this is the so-called linear response formula. In many cases, people just prove this formula. If they have to find the good topologies in which you have convergence, they do something like this reasoning and they arrive to this formula. Notice that here you have first you have to be sure you need that this operator is invertible. This is something that will come from the system, and in particular, it will come from the spectral gap. First, let me make an important remark before this. Notice that in this equation, this guy, since this guy is the linear response is the limit of this difference divided by epsilon. This is a probability measure, this is a probability measure. Hence, the difference, while epsilon goes to 0, the difference is always a zero average measure. So it's a measure whose integral is, the measure of the Wolf space is 0. This is what this kind of measure are called zero average measures. And the linear response is a zero average measure. Is a measure in this space. If the measure has a density, okay? But now we consider only measure having a density, okay? So the linear response will be in the zero average space, but not only the linear response, also this guy is in the zero average space. Why? Because of the same reason. Because L dot F naught is the limit epsilon going to 0 of L epsilon F naught minus L0 F naught divided by epsilon. And again, this is zero average. So here and here, we have zero average vectors. And so this is an equation that must be solved in this zero average space. And this is exactly the space in which we will see the resolvent can be defined. I don't know if I'm saying something very trivial to you because you know very well, but this is an important point. We will see in the next slide. So to have a linear response formula, you have to have the resolvent defined, but you are lucky because you have to define it on the zero average space, and the spectral gap will allow this. The second important point is that this guy, if we define this as an operator on the zero average strong space, it's important that this vector is regular enough to be, oh, sorry, what I mean is that it's not evident what is the regularity of this guy. To be put in this operator, the regularity of this guy must be enough. So it must be something which is in the strong space. And this is not for free. you need you need to prove some regularity of the things. Because of course here is this is a derivative, so you could start from f naught and lose one derivative, so you go into a less regular space and then the resolvent is not defined on this space. So here you need some attention to make things work. Okay, this is just a general remark, but we will see. Yes, please.
So I did not understand why L epsilon F0 has zero average.
Not F epsilon, but well, L dot. So let me write it better. So L dot F naught is equal to the limit for epsilon going to 0 of L epsilon F naught minus L0 F0. So this is the difference of two probability measures. So is in the zero average space. So this guy is in the zero average space. I mean, it's a zero average measure, but it's not. We cannot be very sure that this is regular enough to be in the strong space, because you see here you take a derivative of f naught. So probably you need that f naught is more regular than at the beginning, is even more regular than the strong space. Then this derivative is in the strong space, but for sure is a zero average measure. Okay, so for sure what we can prove is that L dot of f naught is something whose integral is zero. Maybe not regular enough, but for sure it's zero average. And was this the question, or you were asking about this?
Yes, thank you.
Okay, so I repeat the same thing for the linear response. Similarly, the linear response f hat is the limit for epsilon going to 0 of f epsilon minus f0 divided by epsilon. This is something which is again a difference of a limit of a normalization of a difference of two probability measures. So this has zero integral. Maybe I understand the point. Again, this typically is not in the strong space. It can be, but what I was trying to enlighten was that all of these guys, they are zero average measure, but maybe they are not regular enough. About this, we need it to be regular enough because we want to put it in this operator. This we take what we get, but typically we will get a convergence in a weaker topology. So if we are in the situation of expanding maps in which the strong space is the Sobolev space, this guy we will prove that it exists in L1, but zero average, still zero average. Then if you have more regularity, you can prove that this is converging in the space that you like. But yes, you lose some regularity. If you start from something which is very regular here typically you lose one derivative. Okay? Is this answer the question?
Okay, good.
So the point was reasoning heuristically, you expect to prove a formula like this, but to make things rigorous, you have to be certain that this is defined, and you will be lucky because this guy and this guy are zero average, so you want to define the resolvent in a zero average space. But, and then you also have to be certain that this is regular enough to be put in the resolvent. So the resolvent I mean, it's normal to expect that the resolvent can be defined in a kind of zero average space, and in particular defined on the strong zero average space, which is the space of the measure or densities in the strong space with zero average, because in many systems like expanding maps, there is a machinery to prove that there is spectral gap. And more or less what happened is that in systems like expanding maps, the spectrum of the operator acting on the strong space is made like this. There is an eigenvalue 1 with which is having a single eigenvector, which is the invariant density. And then there is something that is called the spectral gap, meaning that there is nothing until a certain disk which is of radius smaller than 1. And the action of the transfer operator can be decomposed into a direct sum, which is, of course, this is the eigenvalue 1, there will be a fixed point, and so there will be a fixed one-dimensional space in our Banach space, which is the space generated by the invariant measure. And the whole strong space can be written as, so this is our fixed point. It will be, it can be written get composed as a direct sum of two invariant spaces, which are the multiples of the invariant measure plus the zero average space. What I mean is that every measure can be written as can be decomposed in this way. And these two spaces are invariant. But if you consider the spectral radius of the operator on the zero average space, the spectral radius will be smaller than 1. And if the spectral radius of this operator restricted to the zero average space is smaller than 1, then you can define an operator which is this Neumann series of power of L0. This will be the resolvent. Now, maybe if you never heard about this, I'm going too fast. But I suppose that more or less you have already seen something similar. I hope. But please tell me, is what I'm writing is completely strange or not? I don't know. I don't know. So, but let me know. Let me. But this is something classical and standard in this transfer operator approach. In the transfer operator approach, people try to prove that there is spectral gap, and by the spectral gap, since this spectral radius is smaller than 1, they can also define the resolvent, and by the resolvent, they can make a sense for this for this linear response formula. Okay, so okay, but in this, so in this term will play the role of the direction of change of your system, and then the resolvent, in some sense, will play the role of the operator that goes from the direction of change of the system to the direction of change of the invariant measure. You can write the formula or even by a sum like this, because the resolvent can be written as a series. Typically, spectral gap is important to write, to have the resolvent to be defined. So, linear response is the direction of change of the invariant, and there is a formula for this, but to establish the formula, typically you need spectral gap and some differentiable dependence of the system on the perturbation. I didn't stress much this point, but you also need to know the regularity, something about the regularity of the invariant measures, because you need this guy to be regular enough to be put here. So you will need something, you may need something about the regularity of your system, of your invariant measures. So more or less, I think that I justified that then linear response happens when you have spectral gap and smooth changes. And this is the case when you take a uniformly hyperbolic system and you change it smoothly. And this was indeed the first kind of system where linear response was proved by a famous by a couple of seminal papers by Ruel. From these, of course, people started to understand if they can relax the assumption, both the regularity and the spectral gap assumption, and people did it in several meaningful examples and family of examples and direction, in particular beyond the uniform hyperbolicity case. So in some sense, relaxing the spectral gap assumption, building complicated construction to recover another spectral gap to prove, which is not the spectral gap on the original system, to prove the linear response for the original system. Another line of research was trying to relax the regularities assumptions and to prove the linear response for system having some kind of non-smoothness, because in the application, many systems are like this. This in the deterministic case. Now, I'm not going to enter in the details. These are the direction in which people prove the linear response statements in the deterministic case, but there is also the random case, which is also maybe even more important in the application, because many models of important systems are random dynamical systems. Let me see. Okay, I think that I'm going really very slow, because I try to do something complicated and to explain it. So let me accelerate a little bit. In the random case, there is something good that happened, which is the fact that the noise sometimes help smoothing things. The noise arrives and creates some smoothing, for which many times you are led to consider as transfer operator some operator having a kernel operator like this. And when the kernel is smooth, the operator is a smoothing operator. And this helps because of the reason that we have seen before. Because, for example, if the phase space is compact, you will have a compact operator instead of a quasi-compact one. So it will help to both to get the spectral gap and the smoothness, the required smoothness. Okay, so then also in this case, there are many, let's say, families of results in the literature, including this quenched random case, which is a case in which you freeze the randomness and you follow a certain random realization, which is quite similar to the non-autonomous case, which I will consider later. But let me go on. And okay, this is about the compactness. Let me just mention a little bit the inverse problems related to the linear response. Of course, if now we know that system has linear response, we apply a certain perturbation, the measure will change smoothly, and we have a formula to go from the direction of perturbation of the system to the direction of perturbation of the invariant measure. And we maybe have many possible kind of perturbation that we apply to the system. And for all these direction of perturbation, you have linear response. You can try to answer some inverse problem. For example, the linear request. Given the response that you want, so given the changes in the dynamical statistical properties that you want to see, what is the best perturbation to apply? And this is also called the linear request, and there are results about this. One similar problem is to fix one observable and then look to the best perturbation in order to optimize the speed of change of this observable. And kind of related question, this is also called the optimal response. Now there is something that also data assimilation, that is finding the best parameter in the system that fit with the data, can be seen as an inverse problem of the linear response, because of course the linear response tells you how the data that you will see will change if you change the system. You can make the inverse step from the data that you have, finding the optimal parameters in the system. And as a last application, I want to mention the optimal fingerprinting, or the fingerprinting problem, which is a problem like this. You see a change in the system, you don't know what caused this change, because you see in the application, you see some observable that start evolving in a different way from they were evolving previously, but you don't see the real system in all the details. So you see a change and you have a set of options, like, is this change caused by the first option or by the second option or by a combination of two or by other things? And of course, this can be related to linear response, because linear response allows you to predict the change. So inversely, maybe you can use linear response to infer what is the perturbation that arrived once you have seen a change in the system. This is the connection, an important connection with climate change, because of course the question that we are trying, that an important question in climate change is what is the main responsible for the climate change and what we can do. So you would like to to understand what is the perturbation that caused what you are seeing in the real life. So, let me go much faster. and start mentioning the non-autonomous case. Non-autonomous case is something like this. Instead of having a deterministic dynamical system where the next state is t of the previous state, always for all n, for all the time, you have at every time a different dynamics. And you may suppose that the system that you are observing was going on since a long time. So you may suppose that there is a bilateral infinite sequence of maps. So the index ranges on Z, governing your dynamics. This is one possible definition of a non-autonomous framework, and this is the definition this is the direction we want to consider here. So we are in the same situation as before, but the map is changing at every time. Of course, since the map is changing, there is not an invariant measure in the sense that maybe there can be no measure which is invariant for all the maps. But in this case, you are led to consider a replacement for the invariant measure, which is called an equivariant family. What is an equivariant family? An equivariant family is a family of measures which is made like this. They start from minus infinite. There is a measure. This is a sequence, a bilateral infinite sequence of measures. There is a measure for every time. And the measure for the next time is the transfer operator associated to the map of the previous time to the next time. Let me say it better. You have a family of maps, you have a family of transfer operator. An equivariant family is a family of measures which is made like this. For example, the measure at time 1 is the push forward for the map at time 0 of the measure at time 0. So you are at time 0, you wait for the next time by applying the push forward and putting the new measure in the next time. Okay? So we are led to consider families of measures to see if we can try to understand the following situation. Suppose you have an initial non-autonomous system, then you change the whole family of maps, and you have an initial equivariant family, and you want to see how, if you have a new equivariant family, and how the new equivariant family relates to the old one, if they change continuously in some sense, or differentiably in some sense, and then you are led to consider the following limit. So it's the same limit as before, but you apply it for all the times, and you hope that this will converge uniformly in the time. If you have something like this will be like the linear response in the non-autonomous case. Of course, why I'm considering the non-autonomous case, because many systems, important systems in real life phenomena are naturally non-autonomous. They change with time. For example, the climate. The climate is subjected to many changes due to the solar radiation, to the volcanoes, to many important things that happen, and they happen at very different time scales. So you cannot say, okay, here I take the average and everything changes and changes in a way that is not predictable. So the best thing you can do is to try to follow, to take this non-autonomous point of view in which you know that your dynamics is going to change at every time, and then you adapt to this. So let me see much time I have. Do I have? Well, I don't want to be too long and to and to make you too much tired. Uh, so what I'm going to do now is to go uh, to show you how this non-autonomous case can be studied. And the answer is it's very similar to the autonomous case, but you have to consider spaces and some new Banach space, which is a Banach space of sequences of measures in which are regular. We will see that everything that I said before, in some sense, translates to this non-autonomous case if you consider the right Banach space, which will be a space of sequences of measures. I show you that at the end you get a formula which is very similar to the autonomous one. Let me just say that this response in the non-autonomous case was something that in the applied science was studied and mostly in particular cases like the periodic case for systems which are usually stochastic differential equations or systems, regularizing systems like this. And recently Valerio Lucarini proposed a general formula for the linear response, for this kind of linear response, and he proved it for finite Markov chains. And also he gave arguments for stochastic differential equation. And what we did in the paper I'm going to talk about is a kind of making this rigorous and making this fit in this transfer operator framework. And then once you have this, you can apply this both to deterministic or random system. And I will give you a little bit a say of some example in which this theory applies. Just let me say that when Valerio proposed his formula, he also tested the validity of the formula on climate evolution models. Now I have not the time to discuss this, but there is this Gill-Sellers model that is a kind of energy balance model that is giving you a model of how the temperature can vary in different latitudes, putting inside the model the solar radiation, the infrared cooling, the unresolved scales. And so it's a kind of simplified model that has some practical meaning. And Valerio tried to test this non-autonomous response formula on this model. He got some quite nice agreement with the simulation. So in this winter, there was some numerical work suggesting that the formulas were correct. This would be interesting to explain, but there is no time. But if you have some question about this, I will be happy to explain. Please contact me. If you are curious, I can explain how this example works. Let's go back to the mathematics. Let's go back to the mathematics. So now let's see how to prove this linear response formula for the non-autonomous case and what is the mathematical framework that we take to prove it. So we have this family of systems that changed in the time. So we formalize this by considering a sequence of operators, which are Markov operators on Banach spaces of Borel measure or of phase space, which will be still X. And the operator will act on strong space and on a weak space. Think about expanding maps, and this is the Sobolev space, and this is L1. And then this operator let the measure to evolve in this way. For example, at time zero, you can have a measure mu zero, which is representing the statistical state of the system at time zero. Then at time one, the measure representing the system will be L0 of mu 0. You apply the first transfer operator and you go to the new state. Then at time 2, you have L1 of mu 1, but mu 1 was L0 of mu 0. So you have L1, L0 of mu 0, and so on and so on. So as soon as you go forward in the time, you have a composition of operators. So you will have sequences of operators that composes like this, and so on and so on. So at the technical level, then the question is, can we understand what happens if we not only, you see, in that case, essentially what people do is, can we understand the iterate, what the iterate of some initial operator are doing on some initial condition? Now, the question becomes, can we estimate how this long composition of different but similar operator do to a certain initial condition, and we understand what is going to happen in the future? When you have spectral gap, for example, what you get is that if mu was zero average, that is, the measure of the whole space is zero, then Ln of mu will go to zero exponentially fast. And the exponential rate is given by the spectral radius of the transfer operator restricted to the zero average space. We don't have the iterates of the same operator, but essentially the main ingredient, I recall, this will be important to define the resolvent. In this case, we will suppose something similar. This composition will go to zero exponentially fast, and we will see that this allows the definition of a new resolvent, which is a resolvent on the space of sequences of measures. And so let me formalize this. This is the assumption that we need is called the loss of memory. This is something classical. There are a lot of studies about loss of memory in non-autonomous dynamical system. But essentially, loss of memory is what we have asked before. We will consider the zero average space in the strong space, and we will say that our non-autonomous system has a loss of memory if, when we apply a composition of operator, the result decays to zero exponentially in the strong norm as the time goes on. Okay? Remark that we are asking for this decay, for this loss of memory, uniformly in the time. For example, if I apply a composition of 100 subsequent operators, I will have a certain contraction of the zero average space, no matter when I start. I can start the composition very far in the time or very far in the future. In the past, in the future, it will be the same. We ask for a uniform exponential decay in the time. And when we have this, we call it exponential loss of memory. We will see that this exponential loss of memory plays the same role as the spectral gap. And this will essentially allows us to make more or less the same proof as before for the linear response formula. And let's go a little bit more in the detail. So we have this family of operators acting on our strong and weak spaces. Now let's define a new Banach space, which is the space. There will be a new space, which is a space of sequences with values in the strong space, a new zero average space, which is the space of sequences of measure, well, all the measures are in the strong space, so they are all random, but they are all zero average. And now we will work with these spaces. Of course, since this is a Banach space, this is also a Banach space. So this is a new Banach space where to try to do things. And we define a kind of new global operator acting on these Banach spaces of sequences. And we will call it big T. This will be the global transfer operator. We define it like this. We take a bold phase V, which is a sequence of measure, and T epsilon of V will be a sequence of measure in which at time n, you have this measure here, which is the measure that you have at the one step before, at the previous time, put inside the previous transfer operator. Of course, this defines a new sequence of measures, and the new sequence of measures make like this. If your initial condition was this sequence of measure, after you apply t, you have this sequence of measures. So at time zero, you have this is time zero, this is the new time zero, this is the new time one, and so on and so on. You have a new sequence. But so you can define a new, let's say, global transfer operator, and an equivariant family will be a fixed point of this global transfer operator. It's also the not but big S, the left shift, because we are in a sequence space, so there is an important operator, which is the shift. We only did this for the notation. And okay, let me skip this. If you hear what is proved is that if you have loss of memory, there can be only one equivariant family in the strong space. And essentially everything will converge to this equivariant family if you wait long enough in the time. And right. And
but you said in the previous slide, you showed how you make it autonomous, right?
yes.
So can you replace the loss of memory? Now we are back to the previous setting. So maybe now we just assume a spectral graph.
Yes. Yes. Essentially, it's like this. What you can prove is that I'm not entering into the spectrum of this guy. I'm going directly to show that the resolvent is defined. Only starting with loss of memory. But if you want, you can restart the problem in an abstract spectral way. But this is not needed, because what you see is that from the loss of memory, you have this contraction, exponential contraction of the zero average space. Directly from this, of course, this means that the spectral radius is smaller than 1. And from this, you can define the resolvent by the usual Neumann series. And you can prove that this is a bounded operator in this space with the topology, which is the small L infinite topology in the sequence space. You are right. This is exactly what one can do. And so, okay, let's take these. Let's take these and remember it because we will use it in the proof. So now the remark is, okay, in this loss of memory situation, we have the possibility to define a resolvent for the global operator. And now we have to ask for, you remember, the ingredient for the linear response are spectral gap and differentiable behavior of the operator. Now we see how to define a differentiable behavior in these sequences of operator. The definition is the simplest one that you can try, the definition that works. You ask for differentiable behavior at every time. You suppose that there is a uniform convergence for this limit to a sequence of derivative operators. And you know that you want to put, you remember, in the autonomous case, what really matters is this guy. So you want to apply this to the equivariant family, which is you proved is unique. So you define this Gn. This is the equivariant family. You define the Gn in this way, and you put all together in a big vector, which is a sequence of measures, and this will be like the forcing term, the direction of change of the system is again will be in the zero average space of sequences. And this will play the same role of this guy. And now let me state the theorem quite informally because I would like to have a little bit of time to show you the proof, which is the same proof as before, but at least to show you that the proof is the same as before. So suppose that you have a situation like this, and then you have a family of non-autonomous systems that change with the perturbation, which is parameterized by epsilon. And for every epsilon, you have a unique equivariant family, which you call Bode phase mu. This is a sequence of measure which is equivariant. And you suppose that for every epsilon in the strong space, you have this bound. They are uniformly bounded. The regularity is uniformly bounded. Then suppose the operator change differentiably, and these guys are all in the strong space. They are regular enough. Then suppose that the system has uniform exponential loss of memory that we have defined before. And also suppose that in the weak norm, the transfer operator is Bauer bounded. This will happen, for example, if the weak norm is L1. L1, every transfer operator in L1, every transfer operator has norm less than 1. So you can compose as much as you want with different operator. They will always be a contraction. The composition will be a contraction. So this is verified easily if the weak space is L1. Under this assumption, you can prove that there is a linear response for the non-autonomous system for the equivariant family, meaning that this family of incremental ratio converge to something in the weak topology. So if, for example, you start with Sobolev spaces, then the convergence here is maybe in L1. Okay, and this tells you that the system behaves differentiably, the invariant measure behave differentiably because there is a limit for the incremental ratio, but you also have the formula, the linear response formula, which is very similar as before. It's essentially the same formula as before. I remarked that this plays the same role of this. So this is the vector containing all the changes in how the change in the operator change the starting equivariant family. Then you apply the inverse shift, and then you apply the resolvent that you have seen that it can be defined because of the loss of memory. And this is the formula. So essentially, it's the same formula as before. Let me show you. Okay, the formula can be written coordinate by this. It is a long it is a long sum. By the way, this is the formula that appears in the initial Lucarini work, and but we discovered that this long sum of different operator and composition is nothing but a resolvent of another map. Hmm? And what is the proof? The proof is very simple. Well, once you formalize the things in this way, you start with the equations defining the measures that you are considering, defining the invariants. Then you take the difference of the two equations and divide by epsilon. Then you play a little bit with the two ends of the equation, and you arrive here, which is the same place where we arrived in the heuristic uh, uh, discovering of the linear response formula before. And then you invert this, and then you get this. Now you have to take the limit for epsilon going to 0. So here you need that this guy will converge in a space where then you can apply the resolvent, and then you need something more, because this is not the resolvent of the initial system, this is the resolvent of the system while it's perturbed. So you need some stability. To have this limit to converge, you also need that these guys stabilize. You have to prove something like this. Identity minus t epsilon to the minus 1 converge to identity minus t0 minus 1. So you also need to prove a stability for the resolvent. This can be done using, again, loss of memory, and then you have the formula. Example of application, and then I would like to arrive to the end of the seminar. The easiest example is you take a family of expanding maps on the circle, and then you take a strong space, the Sobolev space, and then with a weak space L1. In this case, you will suppose that all the expanding maps, they satisfy the same so-called Lasota-York inequality. So they have like a uniform behavior from the functional analytic point of view. This is a kind of standard assumption in the transfer operator approach. And if you also suppose that they are all near to a certain, let's say, central map, then you can prove that this system has an exponential loss of memory. And then from the exponential loss of memory, if you suppose that now you are perturbing the maps by adding a small composing by a small diffeomorphism driven by a certain vector field that tells you how you change, you move a little bit things in your circle, then you can prove linear response in this case. So this is the case in which they are all expanding, they are uniformly expanding, even in uniformly expanding and uniformly regular in N, and they are all near to a certain central map, but you can prove the similar thing if you ask another assumption, which is, okay, they change, they must be always uniformly regular, uniformly expanding, but there is not a central map, they only change slow enough. So you can extend to a kind of slow change of different expanding maps. And okay, this is the simplest deterministic example, but you can also give simple random examples in which you take some stochastic dynamical system in which at every step you apply a certain deterministic part, and then you add some noise which is, let's say, smoothly distributed. And in this case, the transfer operator that you are led to consider is an operator having a kernel. And if you have the noise is large enough, the kernel can be uniformly positive. And this is a source of loss of memory. This is a classical argument in random dynamics, even in finite Markov chains. When the transition matrix is uniformly positive, you know that the Markov chain has a exponential convergence to equilibrium. And in this case, you can prove that because of this uniform positivity of the kernel, given by there is enough noise, by this uniform positivity, you have exponential loss of memory. Then you can do the same machinery as we have seen before, and you can prove a linear response formula for this non-autonomous case. And notice that this is non-autonomous in the sense that at every state there is a random dynamical system. But the random dynamical system may change at every state. The noise may change at every state. The deterministic part may change at every state. So this is really a random system that changes in time. And that's all I wanted to say today. So I gave two examples of application. Here I have a table in which I summarized the comparison between the autonomous case and the non-autonomous case. In the autonomous case, you have the stationary density. In the non-autonomous, you have the equivariant, and so on and so on. You see, there are many. The situation is similar in both cases, and also the proof, as we have seen, looks quite similar. If I had more time and more energy, and you are motivated, but you can look to the preprint. You look to the details of the proof, and they really are similar to the proof of the autonomous case. Okay. I stop here. If you have any question, please, you are welcome. Thank you. I don't hear you now.
Are there any questions?
I have a question.
Please.
You consider the setting in which this non-autonomous dynamical system operates both in the past and in the future, and the past somehow seems important for the setting and for the proofs and so on. So, is there anything that one can say about the case where you only operate to the future, so you don't have the infinite past of the system?
This is a good. Yeah, this is a very good question, because okay, we took this formalization for a non-autonomous system mostly led by a possible application to these climate models. In this case, you need to have to suppose that the system started very far in the past. So our formalization is the formalization when you suppose that you are studying a system that started very far in the past. But for engineering purposes, maybe one can say, oh, I don't care about the past. I start now and I compose operators. In this case, the situation is a little bit, it will be different. For example, it's not trivial in the bilateral case to find equivariant families, because you don't know where to start. You have to start from minus infinity. But in the unilateral case, you can start from a certain initial condition, then push forward this. So there will be many, in some sense, many possible equivariant families. But you can still be interested in, okay, I have this evolution, I change the maps a little bit, what is the change in the evolution? This is a theory that probably I did not really formalize all the. I suppose that this fits with with the with the current approach, but in the sense that you still consider spaces of sequences, but there is also something different because, for example, you don't have uniqueness of the equivariant family. I don't know. I have to think about. But so this is my answer is that I did not really think about this because I was interested in the other case. But this is an important case to understand.
Yeah,
I think
thank you.
sequence framework is the right one for this case, but probably there is a kind of different situation.
Maybe there is another natural extension, you know, but you have to go from one-sided chip to two-sided, like in classical setting. I wanted to ask, because you mentioned this model in climate change, and in that model is the assumption of memory loss fulfilled?
You mean in these Gill Sellers
Yes,
model?
yes, exactly.
This is a complicated question. Uh, 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 so the system itself is an infinite dimensional system to start with. So it's complicated. I don't know. I don't know if people proved this rigorously. I don't even know if people studied this uh, from this point of view. Probably yes, but I'm not expert enough of this model to tell about the original model. Uh, uh, this is a kind of partial differential equation. So the model itself, the original model is quite complicated. But what Lucarini actually did is a simplification. He checked the response formulas in a simplification of this simplified model for the climate, which is made like this. Let me show. He takes a kind of finite dimensional reduction. This I did not explain because I was going fast, but it's interesting what he did. He only considered two observables, which is the average temperature, how the average temperature on the planet. So this is not the average in time. This is the average on the planet. And the difference between the average, I forgot, this delta t is like the difference between the average and the extreme, something like this. Okay, so it takes only two observables, and he consider by simulations. You see, they draw this picture. This is a two-dimensional picture in which you have the two coordinates. So the system is a becomes a two-dimensional system. And by simulation, you know, for example, at a certain moment you are here, then next moment you are here, then next moment you are here, and then you go here, and so on and so on. And here you have a picture of the probability density of the evolution of this discretized system. And this, discretized, let me say, dimensionally reduced induced system. And they discretize even more because they subdivide this space into cells. You see, this two-dimensional rectangle is divided by in many polygonal cells, and then from the simulation, they deduce the transition probability from one cell to another cell. So at the very end, the big system is transformed into a Markov chain. And for this Markov chain, it's much simpler. sorry, is a Markov chain, but is changing in time. And for this non-autonomous Markov chain, is possible to try to see if there is loss of memory and so on and so on. And in this system, they check the linear response formula. But the check is only numerical. There is no proof that the Markov chain that you will have must have loss of memory. This is done numerically by long simulations. So this is a numerical result. But is interesting because it applies to something concrete, to a complicated real world model. So in some sense, one can say, okay, but if you want to they do something about the climate, here you are very far from a real application, because this Gill-Sellers model is already a kind of toy model for the evolution of the temperature. And the model that is considered here is a kind of simplification of the toy model. Okay, but this is why but the real world is very complicated. Mathematicians start from very simplified things. But still, I think even if this is very simplified, this is also interesting because the dynamics is complicated. You see some behavior for these observables, which is complicated, and you see that this is a kind of non-autonomous situation.
Okay, so thank you. This was very interesting. If there are no other questions, let's thank Stefano again.
Thanks to you. And if there are questions, please write me and I will be happy to answer.
Thank you.
Thank you.
Thank you.